Hey, North, Mr. Yurgler here. We're going to talk about hybridization and hybrid orbitals. We've already covered sigma and pi bonds, and we're going to kind of use that as a foundation for talking about hybrid orbitals. There's a few problems with the valence bond theory that we've talked about so far. The theory that says that bonds are formed basically from overlapping orbitals. And this comes from experimental data. So the valence bond theory sounded really good, and we still use it. It's still very helpful. But because of experimental data, we had to kind of modify that. And that's kind of how all of our models kind of get adjusted, right, based on how well they align with experimental data. So we know from experiments that carbon has 4 bonds, and those bonds are equal in strength and in length. This doesn't really make sense from looking at it from a overlapping orbitals perspective, because if we think about carbon's electron orbital diagram, where we have the 2s orbital filled and 2 electrons in the p, and if these are the shapes of these orbitals, where we have the s is kind of spherical and then the p's are kind of these lobes, it doesn't really make sense for electrons to be shared with these orbitals as they are, right? Because you would have to have 2 shared with p orbitals, which are like perpendicular, up and down or side to side, and then somehow shared with the s, which is already full. Even if we think about the 1 electron from the s being promoted up to the p, that would kind of solve that s problem, but you still wouldn't have 4 bonds that are equal in strength and in length, because the s is closer to the nucleus than the p's are. The other problem is that the bond angles don't align with the experimental data as predicted by valence bond theory. We would expect, because these are in the px, py, and pz planes, we would expect the bond, like 3 of them, to be at 90 degrees, and then the 1 from the s being at, I don't know, maybe 180 degrees or something like that, right? But we know from experimental data that all of the bonds are equal. They're all 109.5 degrees. So here's another look at our orbital diagram. And again, even if we promote one electron up to the p, it still doesn't really solve the problem. So how we understand this to work is that they actually hybridize. They take these 2 sublevels in the second energy level and they hybridize them, they blend them into one sublevel that has 4 equal energies. And notice that it's in between the energy of the p and the s, right? So it's kind of like an average or like a blend of the 2. And this would be called the sp3 hybrid orbital, where we have 1 s and 3 p's blended in to make 4 equal orbitals. This can get really confusing, but we're going to try and keep it really simple and straightforward by saying that sigma bonds is always the first bond, and they're always made with hybrid orbitals. I can't really stress this enough. A sigma bond is always a hybrid orbital. Meanwhile, a pi bond is going to be an unhybridized orbital, a leftover p orbital that hasn't been hybridized. And remember that the pi bonds are always the second or the third bond, right? So this single bond, sigma bond, in fact, all of these are sigma bonds, right? Any single bond is going to be sigma bonds. And in a double bond, one of them is sigma and one of them is pi. It doesn't really matter which one. And so then in a triple bond, again, you still have 1 sigma bond and then now 2 pi's. Okay, and remember that the pi bonds are unhybridized, the sigma bonds are hybridized. And this will be very helpful when we go to write hybrid orbitals. There's 3 different types of bonds, and so there's 3 different types of hybrid orbitals that make those bonds. And so you need to be able to identify by looking at a structure kind of like this, or a molecule, based on the number of bonds there are on a given atom, you should be able to say this one has this hybridization. I'm going to switch to a whiteboard to kind of go through this, because I think that'll be a little easier. Okay, let's look first at when we have only single bonds, right? So 4 single bonds. If we have 4 single bonds, then there's 4 sigma bonds, right? If there's 4 sigma bonds, then we have to have 4 equal energy orbitals to use to make those 4 equal bonds. And so I'm going to kind of draw it like this, where we form this blend, and it's going to be in between these 2 energy levels, like this, right? Now, we have 4 electrons and we have 4 orbitals, so they're going to spread out before they pair up. Now we have 4 orbitals that can form 4 bonds that are equal in energy. And we would call this an sp3 hybrid orbital. sp3 because there's 1 s and there's 3 p's that made it up. And it would technically, you could call it that's the 2 sp3 because it's in the second energy level. Now, how does the carbon atom fill these orbitals? Well, remember that there's also an electron coming from each of these 4 hydrogens, right? So the hydrogens are providing these red electrons, which is what's going to form that 1 sigma bond on each of them, right? So this is 4 sigma bonds, and remember that a sigma is hybridized. Now let's look at double bonds. Here we have a double bond. It doesn't matter if it's a double bond to an oxygen or a carbon or any other atom. How many sigma bonds are there in this molecule on this central atom? There's one here. It doesn't matter which one, but there's one of them because the first is always a sigma bond, and then there's two more, right? So we have 3 sigma bonds. Let's take a look at the orbital filling diagram again. Now this is where it's really important to remember the rule that sigma is hybridized. If we have 3 sigma bonds, then we only need, or we're only going to make 3 hybridized orbitals, right? So don't draw a 4th line. The last p orbital is not hybridized, so I'm going to draw it with a little bit higher energy. Now we still have 4 electrons that we can use, and for the 3 sigma bonds, we are going to be making sp2 hybrid orbital. 1 s, 2 p's are making up the hybrid orbital, so it's sp2. Meanwhile, there's still another electron that is shared, but it's shared in an unhybridized pi bond, and that's coming from the oxygen. And so this is your double bond. All right, here's our last example. These are actually going to have the same number of sigma bonds, right? 1 sigma bond here and 1 here, so there's 2 sigma bonds. There's also 2 sigma bonds on this carbon, 1 here and 1 here. So I'm looking at this carbon only. We could say that this is hybridized as well. This one is going to have a different hybridization. This is going to be sp2, like the one that we looked at in the previous example. All right, so here we go again, our unhybridized orbitals, and then we're going to create how many hybridized orbitals? We're only going to create 2 because we only have 2 sigma bonds. So the number of hybridized orbitals, this would just be sp, because 1s, 1p is making it. The number of hybridized orbitals is equal to the number of sigma bonds, right? I'm really trying to stress that. This is what makes hybridization way easier, if we just remember that the number of sigma bonds is equal to the number of hybrid orbitals. Now there's also 2 more p orbitals that are left over that are not going to be hybridized. And then here are 1 hydrogen electron and then 1 carbon electron for our 1 single bond, 1 carbon electron for the sigma bond in here, and then there's going to be 2 pi bonds, right? Whether I'm looking at this molecule or this one, right? In this one, 1 sigma bond is coming from an oxygen, 1 is coming from a carbon, and then the 2 pi's. So the options for hybrid orbitals are only sp3, sp2, and sp. There are more that get into the d orbitals. We're not going to go into that, and so this will keep it relatively straightforward, right? This is single bonds. This is if there's 1 pi bond, and this is if there's 2 pi bonds. And that's really all we need to know. You need to be able to identify if you're given a molecule or a structure, how many sigma bonds are there, and then therefore how many hybridized orbitals would there be as well. All right, this is Mr. Yergler signing off.